that back up 40 degrees with a magnitude of 7, so that our final manipulator configuration looks something like this. And this is surprisingly poorly drawn. So what we would have is, that's a little better there. Maybe not. But anyhow, we would be below the XY plane. We would be at a 37 degree angle about the Z-axis, and we would be shooting off into the, let's see, if this is first, second, third, fourth, we'd be in the 5th quadrant down here.
Move it up.
Oh, sure. So, good. Okay, so let's see if we can't go through and model this with MATLAB real quick. Okay, so what I have done here in problem 3 is I've set up my same frame reference as I have done before. And what we're going to do is use this frame reference to locate the origins of the joints on each successive frame. So we're going to go through and perform the same type of transformations as we have done in the past. Okay? So what we're going to do is we're going to go through and by the way, when you start setting up your function, whenever you're using that function, your path here has to point at the folder that your function is located in. If it does not, you will not be able to access that function, and therefore you won't be able to use it. So what you do is you just select the path that it is located under. And in this case, you will see that right here we have this revolute transformation set up as a function. It has a slightly different symbol set up there. And we can point at it. So I'm going to kind of cheat here real quick since we're running a little short on time. I'm going to copy my revolute transformation from here. And I'm going to go through and define each of these in terms of that revolute transformation. If you notice that I have my DH parameter list here, we define these as 0, 0, 0 because we're on the XY plane, 0, 13, and 7 for our link lengths. And then finally, what were our joint angles? 37 degrees, negative 84 degrees, and 40. 40. Okay, so what I will then do is I'll say that I'm taking the cosine of the angle. Okay, so this is going to be DH arms, let's see, row 3, column 1. Okay, and I'm going to replace theta with that each and every time. And then I see that since we're on the plane, we can point this to 0 for our alpha or DH 1, 1. Let's see, did I catch them all there? Okay, and our radius then will point at DH arms So now we need to multiply that by frame A. Okay, frame B then will be almost exactly the same. Let's see. Or frame C rather. This. There we go. So I'm going to update this matrix for our second transformation. So I'm calling 2, 2, 2. I'm just pulling the parameters out of our parameter list. I could type these in statically if I want, which is fine. However, this will help you kind of get in the habit of using the parameter list to get the job done. Okay, and that's times frame 1. And then we have frame C. Or rather frame D, we just did frame C. Okay, and it's going to be, let's see, we've got this, this, and now we need to do this. Now, do you see kind of the reason why I'm advocating you write a function for this? We're having to go through and call the same transformation over and over again. This is very, very inefficient because we're also at the same time having to manually update the parameters that we pass into this function. So what we're going to do is we're going to write that function for ourselves. That way we don't have to worry about messing this up. I'm sure when I run this, I will realize after the fact that I needed to change something else.
So under frame C, is that supposed to be 3,21 also, or is that just supposed to be 3,2?
Yeah, that's all it fix here in a second.
It's 32.
Okay, so where?
Frame C after your ... negative sign. Yeah.
Right there. Okay, and then I'm going to go through and plot each frame, plot the translations. Let's see what that does for us. Okay, so row 20. Right here. Right there. Oh, that was a lucky catch. Now I just have to go through and fix all of them. And I missed Jill. He would have been able to tell me exactly where all of these were. Have I missed any yet?
Don't believe so.
Okay, let's see if that's all of them. Okay, so in this case, I'm drawing on the XY plane, so let's go ahead and rotate this. Let's see, I need to,
You haven't given it negative parameters.
yeah, it should be good, so,
Well, for the view window.
say again.
The view window doesn't go negative.
Oh, it will. So,
Okay.
I need to label my, yeah, I'll do that real quick. Okay, so now we can get X, yeah, it's showing up on the XY plane, so I need to take a look at my code here and figure out what it is. Unless that's what you were just saying.
Your view axis doesn't give you a negative Z.
Yeah, but that's okay because.
Oh, okay. I thought that's what this was that you were trying
Oh,
to show.
but you're absolutely right here. It's not our point of view, it's the axis
Yeah.
itself that. So, -30. I suppose I don't need to change my X and Y's. By the way, now that I've changed all this, I'm going to have to revert back to previous copy. I'm sure you guys have probably run into this already, but if you use a example for a subsequent problem, make sure you rename it before you proceed, because otherwise it will override whatever you have in that script as you move forward, which is not fun.
There.
Yeah.
Yeah, it's just still not going.
Yeah, I've got a error somewhere in there because it's just not,
It's just on the flat plane.
yeah, it's just defined my, I would imagine that somewhere in here I more than likely copied my alpha into my theta for some reason. But anyhow, tomorrow we'll take a look at setting this up so that we can actually go through and model it. Oh wait, this is on the XY plane. What am I thinking?
Oh,
That's exactly what we want.
Oh, yeah, 'cause you don't have a Z.
Yeah. So in this case, yeah, what was I thinking? Yeah, my drawing that I did just a minute ago was all whacked because we were dealing with a planar robot that was on the XY plane, and therefore it had no Z angle at all. So, real quick, just to fix what I messed up on here, since we're on looking at a planar robot, this is incorrect altogether. What we would see is that we would have a 30-degree rotation about Z, a 37-degree rotation about Z, which would be a 37-degree rotation off of X, followed by a negative 84-degree rotation about that normal. And then we would have 7 units running off here at 40 degrees. So in fact, I'm sorry, we would have a length of 7 here, and the frame attached to the end effector would be rotated by 40 degrees. That makes sense? So that, I apologize about that, I'm not quite sure what I was thinking on the previous example there, so. So anyhow, tomorrow we'll go in and take a look at this a little more deeply, and from there then we'll start to actually develop our code that we'll use for our modeling for our weeks 4, 5, and 6 programming example. This next week, what we'll do is we'll start really looking at motion for our robot in 3 space, and then week 5 and 6 will be looking at trajectory planning for the robot. And that's where we'll go through and start looking at minimization algorithms in order to minimize the distance between the end effector and the destination that we're trying to achieve. So, okay, any questions real quick? Okay, well, we'll stick a fork in it for today, and tomorrow we'll come in and take a look at this again. So.
So I'm doing supposed to already, even though I already know about it, and they told me like what date and everything. Like, does that hurt? No.
Anyone else have homework, or did you guys get it in online?
I just have to finish one of the MATLAB problems, so I'll just print it out and attach it to this. And
Yeah, that's fine. It works out better if it's all together, that way I don't miss part of it, so.
I don't want to do it. Actually, just
Oh, that's fine, so, like I was saying, virtually everything else we do is by programming costs anyhow, so doesn't really matter.
I gotta go to that now. I was in the